All right, evaluate the square root of 81. So remember, this goes back to the question we saw last time. What number multiplied by itself is 81? That's the real question we're looking at here, okay? So this may take some thought, but this is one of the perfect squares that we were hoping that you have memorized by now, but if not, hopefully sometime soon, because it's 9. 9 times 9 is 81. So the answer to that question is just 9. We don't look at just as 9 times 9 is just a 9. Okay, so there's our objective. I can simplify square roots and now cube roots, which is something new for us. But take 15 seconds and copy this down. We'll get started with a little bit of review on square roots. So square roots, we saw this one last time. Remember, we can relate it to a square if we want to. Not that I think anyone really wants to. But there's our square root symbol right there, okay? So when you see a square root of a number, like we see down here, the square root of 100, you could think about it in terms of a square like it's showing on the slide, but really I would prefer to look at it like what number multiplied by itself is 100. And of course, we could think about that for a little bit. But that is a perfect square. We should know that is 10. Okay, so again, last time we saw that it's related to a square. We're not probably going to see that very much. We're going to look at it more in terms of what multiplied by itself is whatever number is inside that square root. So perfect squares, like these ones, the list really is this set right here. Okay, these numbers. You can look at them like this right here because that's kind of how we're going to be seeing these. So today we're going to be using only the first method from last time with the square roots. You are welcome to use the prime factorization method for square roots as well. Remember, as long as you just remember that you're looking for pairs of factors for to create what would be a perfect square. Okay, and again, this is all true. Like remember, this is let's look at something like this one right here. This one's asking what number times itself is 121. Again, that's 11. Or what times itself is 36. It's 6. Okay, so all these numbers right here is what you'd have to multiply by themselves to get these ones. And that's kind of what the first list is showing right there. Okay, so just like we saw last time as well, generally speaking, we're not going to start with two numbers being multiplied inside the square root. They're going to give us an individual number here, and then we have to split it up ourselves into separate factors. Sometimes it's two factors, sometimes it's many factors. But however many there are, you can split them up as you'd like. You can keep two factors in one of these square roots, or 3 or 4, however many you need. So again, more review from what we saw last time. Again, for today's lesson on square roots, I'm only going to be using perfect square factors. However, if you would prefer to use the prime factorization method, you're welcome to do that. We will never require you to use a specific method. So you just choose whichever one you want to. Okay, so for this one, we're going to look for factor pairs of the value, and then we're going to find the greatest perfect square factor among that list, because we may see sometimes that there's many different perfect square factors. We're looking for the biggest one. And so again, we may have to consider that with list. Then we got to take that square root, and then we'll multiply by the square root of the other non-perfect square. So yeah, this list here, we're going to be using this list to see if we can find any factors that would fit into this list here. So let's go to the square root of 40. And again, we're looking for factor pairs of 40. So you're looking at really what we would be considered divisibility rules, right? What is 40 divisible by? Well, it's an even number, so I know right there that's divisible by 2. So I try to start with the smallest number. Some of you guys, I think, would look at the 0 and say it's divisible by 10, which it is, but I'll get there. So it'd be 2 and 20, 2 times 20. And if you didn't know it was 20, just put that in the calculator, 40 divided by 2, it will tell you what the other factor is. Okay, so there's a factor pair. 40 is not divisible by 3, but it is divisible by 4, which is where the 10 comes in. Okay, so is 40 divisible by 6? No, but it is divisible by 5. If I divide it by 5, I get 8. And then it's not divisible by 6 or 7. So then, of course, you could say 8, but we've already got the 8 there. Okay, so these are the 3 only factor pairs from 40, other than using 1, which we don't really want. Okay, so let's go back and let's look at the list. Okay, so here's our list. Do we see any of these factor pairs in this list? Yeah, I see 4. There it is, 4. Are any other numbers in this list right here? Nope, there isn't. So that means I can't use that factor pair set or this one. And 4 is the only perfect square factor of 40. Okay, so I'm gonna take my square root of 40. I'm gonna rewrite it as the product of two factors, which I already have there, 4 and 10. Okay, and even this allows me, so let's take this out so I have some space, to now take that and I can split it up. Okay, so I'm gonna take my 4 and 10 here. I'm gonna rewrite it, but I'm going to split these up. Okay, square root of 4 and times the square root of 10. But again, the square root of 4, we see that over here is just 2. So square root of 4 is 2. Now I'll multiply that by the square root of 10. Boom, simplified. That's it. So I use this perfect square method, but you can use the prime factorization method if you prefer it, all right? So how about this one? So remember from this, just like we saw last time, I'm pretty much ignoring the 3 until I finish with simplifying the square root of 48. Okay, so let's look at factor pairs of 48. Again, I'll start with the smallest one I know of is 2. It's divisible by 2 because of the 8 in the ones place value is even. So if I divide it by 2, I'd get 24. Okay, is it divisible by 3? Yes, it is. How do I know? Because 4 plus 8 is 12. You can just add the digits. If that number is divisible by 3, which 12 is, then it's the original number is divisible by 3. Of course, you could have just put it in the calculator, but 48 divided by 3 is going to be 16. And that's pretty good. Is it divisible by 4? Yep, it is. That'd be 4 and 12. And you see how these numbers are getting closer together. We want them to get as close as possible together. Is 48 divisible by 5? No, but it is divisible by 6. That'd be 6 and 8. And then it's not divisible by 7, but again, 8. Well, we already have that one. Okay, so this is all of our factor pairs for 48. And again, just don't forget that the 3 is there. We'll apply that at the end. So let's look at our list and see if there's any numbers in the factor pairs that are in this list. Well, there is. In fact, there's 2 of them. We got 16 and 4, right? 16 and 4. But again, we're focused on which one's bigger, and that would have to be the 16. Okay, so I am not going to be using the 4, and that, of course, we're not going to be using the ones that are not perfect square factors. So let's go back and take that square root of 48. We'll apply the 3 later, but now I'm going to write it as the square root of 16 times 3. And just like we saw in that last problem, I'm going to take these two factors, 16 and 3, and I'm going to split them up into their own square roots, like this, because the square root of 16 we see here is just 4. So now I have 4 times the square root of 3. Okay, now that is just the simplified form of the square root of 48, but now I will go back and look at this 3 and apply it to all the work that I have, because it was always being multiplied there. So in the end here, it's still being multiplied by 4, and I can simplify that. 3 times 4 is 12. Well, still multiplied by the square root of 3. Done. And do keep in mind, some students have been forgetting to put this 3 part in a square root. It needs to be in a square root because it came from the 48, which was also in the square root. So hopefully those 2 examples kind of emphasize the importance of having the perfect squares memorized, right, from this list right here. And in fact, this next one, we can see that we have the square root of 49, which is also in the list right there. So I can just take that square root of 49. Yeah, try not to overcomplicate this. 49 is already a perfect square for 7, and so I can just keep it there. And so I really end up with 4 times 7, which is final answer here, 28. That's done. All right, now this brings us to cube roots. Now you'll see up here with the cube root symbol here that it's the same square root symbol, but now they have what we call, this is an index. Not that I think you care, but I may be using that vocabulary a little bit more often than I'd like. That's an index, 3. Okay, so where square roots we needed pairs of values when we're using prime factorization. With cube roots, we're looking for 3s, matches of 3 or triples, in order to pull them out of the cube root. That is what will create for us a perfect cube. Okay, so You could also call this a third root, but I guess it's just faster to call it a cube root. But it comes from cubes, if you care. So, like if you were to make a cube, let's pretend like I'm drawing really nice cubes, really pretty ones. Okay, so if I do this cube, I'm making a cube. Or what I'll pretend to be is a cube, okay? So then we're just gonna connect the corners here, make this look pretty. Yep, there it goes. Okay, so there's a cube, and we'll pretend like it's pretty, even though I did use technology, so it's a lot better than what I would have drawn. But what's unique about a cube? Well, a cube is gonna have all of the faces or surfaces are squares. So all of the edges on here are the same length. Okay, so if for some reason you wanted to find the volume of a cube, it's side length times side length times side length, like this. Or you can just write that as side length cubed. And so for these types of problems, and again, I don't know if you care about this stuff, I'm just kind of giving you the background why we call it a cube root. It's just like starting with the volume and then trying to find the side length of whatever cube is, okay? So if for some reason they'd given us the cube root of, let's say, 1,000, like this, and that's how this reads. That's the cube root of 1,000. But the question here is saying what number multiplied by itself 3 times is, in this case, 1,000. And yeah, for some of you that know that answer, it is 10, okay? So in other words, if you had a volume of 1,000 for a cube, what's its side length? 10, that's it. Okay, so again, I prefer to look at it more with this question, what number multiplied by itself 3 times is the value, in that case, 1,000, but that value is gonna change, all right? So with cube roots, there's no expectation whatsoever for you to memorize perfect cubes. And just like with the perfect squares, we could use a calculator to find those perfect squares. And so we're pretty much going to use essentially a calculator to do this as well. Now, calculators won't simplify cube roots, but they can help us with the division part when we're looking at the prime factorization, which is what we're going to be doing. So right here, this one is saying what number multiplied by itself 3 times is 125. And I think some of you may even be able to do that in your head. If not, don't worry about it. But here's what I know. Okay, so I'm looking for some prime factorization right here on this one. I'd say, look, 125, I know it's divisible by 5, and that is prime. Okay, well that, again, you can just throw out the calculator, 125 divided by 5, that's 25, which splits up into another set of 5s, okay? So in other words, the cube root of 125 could be written as the cube root instead of 5 times 5 times 5. So again, what number multiplied by itself 3 times is 125? It's just 5. Okay, so in other words, 125 is considered right here a perfect cube. Well, let's say you didn't want to do it that way. Well, 64, like we'll see, is kind of a perfect cube. And so if you wanted to go through them, which you could do, you could say, well, I know 1 times 1 times 1 is 1. 2 times 2 times 2, that'd be 8. 3 times 3 is 9. Times 3 is 27. 4 times 4 is 16. And then times another 4, boom, there's the 64, okay? So just this cube root of 64 business, that's going to give us 4. In other words, what number multiplied by itself is 64? It's 4. But just like we saw with the square roots, this negative here in front, now I apply it to the answer at the end. I apply it at the end, and that is all I got to do right there. Okay, so the final answer on this one is negative 4. Okay, so something like this one. Okay, so the cube root of negative 27. So again, what number multiplied by itself 3 times is, and we can show this as negative 27. With the square roots and the negatives on the inside, that was no good. But you can have 3 negatives being multiplied to get a negative number. That's okay on this stuff, okay? So, what number multiplied by itself is negative 27? Well, 27 we know that would break up into, I guess, 3 and 9. 3 is prime, and then 9 breaks up into 3 and 3 like this, right? But if I were to make each of these 3's negatives, that would be okay too, which means that what number multiplied by itself 3 times is negative 27? It's negative 3. And that's shown with the prime factorization. I didn't show as many steps as I did on the first one because this one kind of came pretty clear right there. Okay, so there's all 3 of those. But again, just especially if they're perfect cubes like these ones, yeah, we kind of ask ourselves the question, what number multiplied by itself 3 times is whatever the number is. But we're not going to have that luxury with some of these other problems. We're going to actually have to use the prime factorization, kind of like we did on that first and third one. Yeah, we had to change that word. Find all, it's not pairs, it's triples of prime factors. Because the index here is 3, that tells us we need 3 matches in order to make what would be considered a perfect cube, okay? So we'll find all the prime factors, and for the most part, we're not going to see prime factors beyond 11. So expect to see numbers like 2, 3, 5, maybe 7, maybe even 11, but not usually anything past that, like 13, 17, 19, and so forth, okay? So we're looking for these prime factors. Remember, in a factor tree, we're just kind of circling those to show that it ends the branch. And once all the branches are ended, then we know we're finished with the prime factorization tree. Now, we kind of combine those into one individual large cube root. But again, we're looking for triples, so we will even order them so that numbers that match are close together so that we can identify the triples. If we find any triples, then we pull those out as perfect cubes. Any non-triples just stay inside the cube root, like we saw with square roots. So the cube root of 27, right? So again, what number multiplied by itself 3 times is 27? Let's write that out. What number multiplied by itself, and again, it's 3 times now because of the index of 3, in this case is, this one's positive 27. Okay, so it's a little bit different, but pretty much the same. So the prime factorization on this, 27 divided by 3 would be 9. So 9 splits up into 3 and 3, right? So showing more steps here. Not that I think you want them, but that'd be the cube root of 3 times 3 times 3. So I see a triple right here with the index of 3. So it just drops out as a 3. Boom, it's done. And yeah, I think some of you guys would have seen this right here and just written 3 here. But I was showing that extra step, okay, because I found a triple 3. So 192 is not a perfect cube, which means that we're going to have to go straight into prime factorization on this stuff. Okay, so let's go ahead and start that out. I know just right off the bat that 192 is divisible by 2 because of the 2 and the 1's place values even. So I can divide that by 2. Again, if you need to use the calculator to do it, but that should give us a 96 right there, which is also divisible by 2. So 96 divided by 2 would be 48. Which is, I'd say, I would probably split this up between 8 and 6, like this, and then 8 splits up into 4 and 2, which is 2 is prime, and then 4 splits up into 2 and 2. Okay, 6 splits up into 2 and 3, though. Okay, and that ends all the branches. There's a lot of factors for 192. That's not a problem. We'll rewrite 192 not as 192. It still has the same value, but as the result of its prime factors. So how many 2's, and again, for my factor tree, the 2's aren't all next to each other, but I'm going to line them up in the list of factors being multiplied in the cube root so that I can find triples. So I'm looking at the 2's. 1, 2, 3, 4, 5, 6 2's, right? 1, 2, 3, 4, 5, 6 2's, and then that kind of odd 3 right there. But what we want here is we want to take these and find triples, right? So there's a triple 2 right there. So that means that I would then have the cube root of 3 2's multiplied together. 1, 2, 3. And this will be multiplied by, well, what do you know? There's another set of 3 2's right there. So we can take that and multiply it by itself again. Okay, a little bit more space. But then you notice that at the end we have this 3. Remember, that still stays in a cube root, but I have to write it separately here, okay? All right, so this is my new setup. I'm allowed to break these up with cube roots just like I was able to do it with square roots, okay? So what do I got? I got this set of 3 2s, which would give me a 2. It's 3 2s. Here's another set of 3 2s, which is another 2. And then my cube root of 3, still just cube root of 3, because it doesn't have 3 numbers multiplied to get itself together to get 3. And don't confuse that with 1, because some students do. It's like 1 times 1 times 1 is 3. No, it'd be addition first, but we're looking for multiplication, right? So right here, I see I got 2 times 2, which is 4. And then I can still multiply that by the cube root of 3. And I believe on the assignment, from what we saw last time, they did require the multiply symbol. Maybe not, I forget, but you may have that required. On the assignment that we have, the cube root button is just a button that you push, and then you enter the 3. Let's try this one then. So 2 times the cube root of 135. So just like we saw with the square roots, I'm going to ignore the 2. I'll come back to it, but I'm going to ignore it for now. So let's split 135 up using some factor tree business, prime factors. So just with the 5 in the ones place value, I know it's divisible by 5. So in the calculator, 135 divided by 5 would be 27. Okay, now 27 is a number we've seen a few times already. That would break up into 3 and 9. 3 is prime. And then 9 breaks up into 3 and 3, okay? So I'll come back to the 2, but I got the cube root now of 1, 2, 3 3's being multiplied, and a 5. Okay, well, this allows me to break that up into the cube root of 3 times, I'll use this, 3 times 3 times 3, and then, again, that's still being multiplied by the cube root of 5. Okay, so it's still being multiplied. But we have this triple 3 right here, which means that what number multiplied by itself 3 times here is it's 3. And I guess that would have been the 27. Okay, so we'll still multiply this by the cube root of 5. But now that we have that cube root of 135 simplified, I can go back and I can apply this 2, right? It would have been there multiplied by that cube root. It would have been here in front of these 2 cube roots being multiplied. And so therefore, it is also in front of the 3 that we pulled out right there. So we'd have to do 2 times 3 here to get 6. And it'd be 6 times the cube root of 5. Boom. About as simplified as I can make it. That brings us to the objective. I can simplify square roots. Square roots, if you use prime factorization, remember you're looking for pairs. Cube roots now, though, if we're looking to simplify square root, cube roots rather, we're looking for triples. They have to be matching sets of 3.